Hey kids, welcome to another day of statistics. We are going to talk about the normal distribution today. Remember, in previous videos, we talked about looking at a set of data and seeing whether it was, again, there's lots of distributions, but we determined between skewed right, skewed left, and normal. So we're going to focus on the normal distribution. We're going to talk something about z-scores, finding a z-value, finding a p-value, and we are going to be using your calculator. And we're going to be using the stat capabilities of your calculator. So make sure you have this handy. Again, if you can do it with a computer or a website, that's great, but you want to get used to the keystrokes on your calculator for our assessments and IB assessments. Okay, so the normal distribution, remember a normal distribution, when we're talking about even discrete data and we kind of make a curve go over it, or continuous data, right, where you have even tails, right? Even tails here. And it's very symmetric across the middle. So it's called normal because it occurs most often, right? So anything that, anytime, anything that you see, right, that's really what the word normal is. People misuse the word normal, but normal just means I'm used to it, right? So if I'm used to getting up at 9 o'clock, or getting ready for class at 9 o'clock, and so I just need to come up to my room as soon as somebody changes that, it's not going to feel normal anymore when I have to go to the school building at 7:45. Or 7:25 for me. Boo. Right? Doesn't feel normal anymore until I go to the building every day at 7:25, and then after a certain amount of time, that'll feel normal too. So what's normal just means what occurs a lot. The normal distribution does occur a lot in our world, right? Data does tend to be, especially if you have a large set of data, it is distributed normally. Not everything, but many things. So if I give you this data, maybe take a picture of it or whatever, you certainly don't want to copy all of this down, but in your notes, you want to have this or print out this slide or something from this just table, right? This chart. I hope that you can see that this is a normal distribution approximately, right? It doesn't have to be exact. I mean, I'm just eyeballing, just by eyeball, right? I start off low, I end off low. Somewhere in the middle here, there's a peak. And I'm building to the peak, and then I go away from the peak and tail back off. It's not exactly, right? But it's pretty normal looking, even without a graph or a picture or that bell-shaped curve. Put this data into L1 and L2 and run your one variable stats with L1 and L2 so that you can calculate the mean and standard deviation. I got 10.68 and 3.67. Where did I get that? 3.87. Right, let me do, 10.68 and 3.87. Okay, so 10.68, that sounds right, kind of right. I believe that my mean is 10.68. Don't have heavy outliers, right, skewing the mean away from the median. Now they asked me to calculate the distance from the mean and one standard deviation to the left. Then they asked me to calculate the distance and one standard deviation to the right. So mathematically, what is that? That is taking 10.68 and adding or subtracting 3.87. And when I did that, I got 6.81 as one standard deviation below the mean. And remember what the standard deviation is telling you, right? It's that sum, it's that one number to kind of represent the average spread, if you will. So a little bit shorter than 4. So I got 6.81 and 14.55. So now let's look at our chart and estimate the number of scores between one standard deviation below and above the mean. So 6.81 somewhere here and 14.55 somewhere here. So add up the frequencies that you have in between there. So I have 31 plus 49 plus 38 plus 28. And I got 146 out of that. Is that right? 16, 10, yeah. 146. Now look at the next part. What percent? Percent. So what am I dealing with? What percent of the total of 213, where did I get that from? Added all my frequencies together, are between one standard deviation of the mean. And that, remember, means plus or minus. Well, look what I just found out. 146 is the number of data I approximated between, right, one standard deviation below and one standard deviation above the mean. And what, to get a percent, what am I going to do? Divide that by the total. What am I going to get out of that? Those of you that are AP Stat are not going to be surprised by this number. If you are normally distributed, almost 70% of your data falls within one standard deviation of the mean. Crazy, right? Kind of cool. All right, so let's talk a little bit. Now you have a note sheet with the normal distribution. So these next slides follow right along that. The probability density function, or probability density curve, meaning continuous, has the following properties. The mean is at the peak. It is symmetric. It only has that one peak in the middle, and it is bell-shaped. So the mean and standard deviation completely specify our normally distributed random variable. Here's some notation that you don't need really, right? Yay, this is fancy math. Random variables, approximately the norm, blah, 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 blah. Don't care, don't care. Here's what I need you to focus on. In your notes, please highlight this. Standard normal distribution, right? I'm going to create a standard. After all, when I have a set of data like what we just did, right? I found the mean to be 10.68 and the standard deviation to be 3.87. I want to be able to take those numbers and standardize it so that another set of data who has a mean of 50.2 and a standard deviation of 8, but both of them are normally distributed, I want to be able to standardize both of those statistics so that I can operate mathematically with them as if they were the same. And how I'm going to do that is I'm going to take whatever mean you have. Remember, our mean was 10.68. I'm going to pretend that that mean is 0. We had one standard deviation that was plus 3.67 to the right and minus 3.67? 8? I don't know why I keep writing 87. I'm going to pretend, I'm going to say 10.68 is the same as being 0. One standard deviation above the mean is going to be a plus 1. One standard deviation below the mean is going to be a minus 1. That's what it means to standardize normal data. So, of course, I need to have normal data first. You're always going to turn the mean, wink, wink. Whatever your mean is, you're going to consider it 0. Whatever your standard deviation is, you're going to consider one standard deviation is going to be equal to 1. Now, since this is a continuous curve, just like you don't need to know this is swell, you also don't need to know this. But this is swell and it's really cool. Okay. So just if you don't want to do this, I'm never going to test you on this, right? But just as an exploration, since we have time, it is a video after all, I want you to put this function into y1. 1 divided by the square root of 2 pi, e to the, and make sure this is all up in exponential land. And then I want to make your window this. Make your x min and max and your y min and max -5 to 5 and -0.5 to 0.5. And if you hit graph, you will see this curve. Isn't that kind of cool? It's an e to the, so you know e to those, right? As you go off to infinity or zero, approaches zero. But because I have an e to the squared, I have the same thing on both sides. And then this is just the leading coefficient, right? This is just the multiplier in front. The dilation factor, if you will. Now, here's what I want you to do. You ready? You know what to do if I wanted you to enter some number, right? If I wanted you to find a point on here, right? You do second trace. Well, I want you to hit second trace, right? Which is to get to calculate, right? Hit the second button and then hit the trace button. Normally we use value, right? If we just want to find a value, or we use 0, we used min, we used max, we used intersect. Intersect. We have not used choice 6 or 7, dy dx, or that weird thing, right? Curly SF. I want you to choose 7. Second trace 7. What happens when you do that? What's it ask you for? It asks you for a lower limit. So what I want you to do is I want you to hit the lowest limit of the graph that we have, the lowest x limit. It won't let you go beyond that. So I want you to hit, what's our lowest x? What I tell you to make your x min? -5. So hit -5 for the lower limit. Then hit enter. What does it ask you for now? The upper limit, right? Hit 5. What does it do? Oh, snap, it colors under there. What does it tell you that curly fx dx is equal to? Oh, snap. What the calculator just did is estimate something you'll know how to do next year, which is actually calculus, which is find the area under this curve. And the area under the standard normal distribution curve is 1. That area is 1. That's where all our probabilities come from. Hey, hit, now you have to do something to get it to clear the drawing. So if you hit second program where it says draw, second program, and then hit choice 1, it'll clear your drawing. Now do this again. Repeat this. Do second trace 7, but this time make your lower limit 0. And your upper limit 5. What's it really close to? A half, right? This is where our probability distributions, our z-scores, this is where this all comes from. It is calculus, okay? Because it all leads back to calculus eventually. Pretty cool. So first I want to talk about, before we get back to that, I just want to talk about if I change, I mean, I can do, you've been doing translations for a long time. So if I change, right, if I change my mu, this is without standard. If I change my mu, my curve goes right or left. If I change my lowercase sigma, my standard deviation, I control the spread. So this picture is in your packet, and it talks about like looking at, right, all three of these are with a normal, right, our normal mean of 0. So hopefully you can see all three of those curves where I control the spread. If my, right, variance is 0.2, notice this is variance, not standard deviation. Variance of 0.2, variance of 1, here's my normal. Right, because the square root of 1 is still 1, right? These ones are not normal, standard normal. Still a normal, all of them are normal distributions, right? Can you see that? They're all normal distributions. But this one is our standard normal because mu is 0 and the mean is 0 and the standard deviation is 1. Okay, cool. And hopefully you can see here, right? I have a very large spread. Here I don't have much of a spread. This green one is the shift left when I change my mu. Okay. All right. So we are going to do more with applications in the next video. But just to kind of set up the, as I said before, many things that we measure in our human world, right? If you collect a large enough data set, it falls out in a normal distribution. Nature, disease. So again, those of you that are in AP Stat, you either have or will have talked about the central limit theorem. If you don't take AP Stat, right, it's not a big deal. You won't be asked about the theorem per se, to name the theorem or anything like that on an IB exam, but there are some components that you do that it leads to. The empirical rule, this you do need to know. If the data follows this rule, and by this rule I mean 1, 2, 3. If you know these 3 facts, then you can assume you have an approximately normal distribution, which means you can then standardize it, which means once it's standard, you can apply a whole bunch of calculator and table approximations to it and do a whole bunch of really necessary statistics on it. So this whole division, 68.2% of your data fall within 1 standard deviation. That means plus or minus 1 standard deviation of the mean, plus or minus 2 standard deviations of the mean is where 95.4% and very small amount fall within 3 standard deviations of the mean. If this is so about your data, then you can assume you have an approximately normal distribution and a whole bunch of math opens up to you. So here is again our normal distribution curve. You know the equation for that. It's in your calculator. So between plus and minus 1 standard deviation of the mean, this total is 68.2. And again, these are all approximate numbers. Between 2 standard deviations of the mean, if you add 68.2 2 times 13.6, you're going to get 94. 95.4. And then within 3 standard deviations of the mean, you have almost 100% of your data. This is the empirical rule. So let's use this. Remember, this is approximately normal. That's all. If we can measure this, we can say we have an approximately normal distribution. So how are we going to use this? Here are your keywords. Army, distribution. There we go. That is important. If I know the data is approximately normal, then the empirical rule holds. Sometimes you have data, you look to see if the empirical rule holds to say I have normal. If you are given normal, then you know the empirical rule holds, okay? So, given normal, then empirical. So they're giving me my mu, and they're giving me my standard deviation. Use the empirical rule to answer the following. So they want a percent between. They want to know a percentile given a head circumference. They want a percent of greater. Okay, so those are my keywords. So let's go attack each one of these. So 21.7 and 23.9, what is that? Well, if my mu is 22.8, what is plus or minus 1.1 inches? Well, 22.8 minus 1.1 is 21.7. And what is 22.8 plus 1.1? Ah, what a quinky dink. I think not. So what percentage of soldiers have a head circumference between 1 standard deviation of the mean? Using the empirical rule, I don't have to do any math, right? Close to 70%. Close to 70%. Now, check out the next one. A head circumference of 25. So a head circumference of 25. All right, do you see this picture I've put down here? Let's go down here and enter our data. Our mean is 22.8. 1 standard deviation above the mean is 23.9. What's 2 standard deviations above the mean? What are you going to do? You're going to add 1.1 and you're going to get 25. Oh, snap. 25 is one of the things they're asking me about. Certainly, I knew 25 was above the mean. So I started saying, well, if they want a head circumference of 25, where am I on my bell curve? Oh, I'm right here. I'm at the standard deviation. So if I'm at the standard deviation, what's my percentile? Your percentile comes from your area under the curve. Remember, this total area is 1. What is that, right? All that shading under the curve is 1. It's unitless, but 1 unit, kind of like your unit circle, right? Well, what is 1 as a percent? So all of these shadings are part of 100% or a decimal smaller than 1. So when they are asking me for the percentile, they are just asking me for how much of the curve is shaded up to that point. OMG. Well, what is that? Well, I just showed you, I mean, there's a variety of ways to get this, but how much is this shading? Up to the mean, how much is that? That's half, right? That's 50% or 0.5. Then what else do I have to add? What's that? And then what do I have to add? OMG, add those 3 together. And I got 0.977. Or as a percent, but they asked me for the percentile. The percentile is just the right? Just percentiles out of 100, right? The decimal representing the area. What about this then? Can you see how part B is going to help me answer part C? What percentage of the soldiers have a head circumference greater? Well, since I already know the position of 25, I just have to figure out that. Well, what is that? That little black shading is 1 minus all my other shading. Right? You might want to know this when they are ordering a bunch of hats for the soldiers. There's not very many soldiers that are going to have a head circumference above 25 inches. Don't order too many of those size hats. Right? Cool. All right, so Z-scores goes to, like, I just dealt with that problem without standard. I dealt with the Army problem just using the empirical rule, knowing that they told me the data was approximately normal. Z-scores go with standardizing. Spell standardizing like that. Standardizing a normal or approximately normal distribution. So a Z-score means, oh, do you see how I got my text to be my Mario coin side? I was so excited about that. All right, so if data lies 1 standard deviation above the mean, we call that having a Z-score of 1. So in the Army example, the 25, right? That was my position of 25. I would have called that a position of 2 because the data point 25 lie 2 standard deviations above the mean. So a Z-score is just the coefficient, right, if you will, in front of, when you're talking about cutting and slicing up, in front of the standard deviation. Those are just for the slices, but how do I get a Z-score anywhere? The formula, you do need to write this down and you need to know this. The formula for these z-score is x, which is your piece of data, sometimes called z sub 0, minus the mean of the data, divided by the distance from the mean. Right? So data minus the mean over standard deviation gives you the z-score, and the z-score says how many standard deviations away from the mean is your piece of data. But it's also a probability, right? Notice that I can have a z-score that is positive, right? Because the standard deviation is always positive. Standard deviation is, oh, that's not what I wanted to do. Standard deviation is always positive, but your numerator is a difference. So if your data is greater than the mean, then data greater than mean minus the mean will be a positive over a positive. Your z-score would be positive. But if your piece of data is less than the mean over the standard deviation, which is always positive, minus the mean will be a negative over a positive. So a z-score can be negative or positive, meaning left or right of the peak, the mean. So here we go. Sample of record albums, blah, 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 blah. If they are asking you about a z, if they are asking you about a z-score, you have to have normal distribution, right? So they don't have to say that. So sample of record albums, they give me the mean, they give me the standard deviation. Find the z-score. So 0.877 minus the mean. Each one of these is going to have the standard deviation on the bottom. Which one of these are going to be positive? Which one are going to be negative? There's my normal curve. Here's my mean. 1, 2, 3 standard deviations. 1, 2, 3 standard deviations. My mean is 3.05, but I consider that the center or my zero. And then 1, 2, 3 standard deviations, -1, -2, -3 standard deviations below the mean. So my data piece here is 4. Z is going to be positive. 2.5, Z is going to be negative. 5, Z is going to be positive. So what did I get here? If you do this just on your calculator, you get 1.08. What does that mean? My data is 1.08 standard deviations above the mean. Where is that? About right there. There's my z-score of 1.08. Notice that my piece of data, 4 minutes, is in the right? Right outside the 70% using the empirical rule, right? Of where most of the data is. How about 2.5? If you do that calculation, your z-score is going to be negative. So my little strip is going to be below the mean, right? I got negative 0.677. Where is that? About right here. How about 5 minus? This one should be a positive number. And I got 2.72. Way over here is where that strip is. All right, so that's kind of cool. All right, so a z-score is just a strip, right? An x value, if you will, right, along that horizontal axis goes with this, and think of that strip as having, right, no, it's a line. It has no width. Okay, it is just indicating a position to the right or to the left of the mean and kind of how far. And since I'm normal, I can kind of say to myself, well, you're up there, right? You're up there in the top. Oh, you're a little below the mean, but you're still within like that in most of the, almost 70% of the data kind of thing. Now let's move to oh no, before we do that, I'm sorry. I don't want to move. I still want to be talking about z-scores. So I want to talk about the highest relative score, right? And they all are taking different tests. This is the idea between why I want a standard. Why do I need standardization? Well, what if I want to compare students that take a different test, right? So I have one test with an average of 50, average of 84, average of 300. Obviously, these are different tests, but they're testing the same thing, the same neuroticism, whatever that is, right? So I want to compare student 1, 2, and 3. So I can say, well, where is this student? And again, if we're talking z-scores, we are dealing with normal. So each one of these has a different mean, but it's the same normal distribution with the same area of 1, right? So this standard deviation is 12. Where is that relative to this curve? Well, your z-score standardizes your results so that you can compare all 3 kids even though they took a different test. So 36 is going to be a negative score. 72 is also, I wrote 50 there, but I meant to write 84. This is also going to be negative. 255 is also going to be negative. So what did I get here? Do this on my calculator. I got negative 1.16. How many I don't care that the standard deviation is 12. How many of them are you away from the mean? Negative 1.16, so about here. How about the second student who took a test where they got a 72 on a test whose average was 84? It was negative 1.2. And the third student was negative 1.5. So do you see how the standardization let me negative 1.2 is about there. Negative 1.5 is about there. So vastly different tests, but testing for the same objective or outcome, if you will. And all of them performed about the same, right? Given a normal distribution, they all performed about the same. So who had the highest relative score? Well, the one that was, in this case, since they were all below the mean, the one closest to the mean. Right? Do you want to score high on a neurotic test? I don't know. Right? But each one of these was a little bit further away from the mean than the first student. Even though it looked like, oh, well, a standard deviation of 12, what's going on, right? All right, now I want to move on to this idea of p-values. Getting probability from standardized scores. Okay. So the probability is linked to that idea of the area. Area under the normal distribution. And remember, what we're going to do is think about that area. That total area is 1, which goes with 100%. So we are now going to think about z-scores as a boundary, and we're going to talk about how much area is above or below our boundary, which is a decimal less than 1, which we can turn into a percent. What? So on your calculator, this is how we're going to use it. I'm going to describe what it is, and then I'm going to show you how to use it. This is to find the normal. Pay attention to this C right here. You're going to go to second vars where that distribution is. Right above vars, it says distribution. So you're going to hit second vars, not choice 1. You're going to choose choice 2, the normal cumulative distribution function. You do not have to worry about this. You do not have to enter 0 and 1, because as long as we are dealing, we are not going to shift. Remember that we're at the beginning there, I showed you right, I can shift mu or shift or mess around with my standard deviation. As long as you are not shifting your mean, not adjusting your standard deviation, you don't have to enter this. The calculator assumes 0 and 1. So you don't have to enter this. All you have to enter is A and B, and I will describe what that is for you shortly. So assume that I have a normal distribution. You always want to do this. Trust me, there's not going to be any points for your drawing, but trust me, this is going to help catch silly errors. Sketch the normal distribution and shade the p-value that you want. Then you're going to be able to get the answer with your calculator. So I'm going to do a silly one first. Hopefully this is a duh. So I'm going to sketch the normal distribution. Come on, pen. Pen's freaking out here a minute. There we go. I don't have to make a great drawing. Okay, that's kind of terrible. What is the probability that my z-score, which corresponds to my data, right? It's the standard data, lies between -1 and 1. Well, what does that mean? This is area. Whoops. Okay, that's all of it, I hope. Duh. How about this one? I hope this is also a duh. I guess I should say score, sorry, z-score. It corresponds with area shaded between those. So remember, you have a mu of 0. This is 1, 2, 3 standard deviations away. But remember, your z-score is going to give you a position here. So what's the probability that I am going to shade greater than 0? Remember, we're considering mu is 0. So without a calculator, what's the probability that your z-score is going to be above 0? Well, there. Whoops, I am so sorry. I was jumping ahead, and I did not do that right. I was thinking 1 as the area, silly, where between 1 and 1 is here. Right? So my z-score between 1 and 1, that's going to be, right, my 68. That's just my 68.2, my 68.39, whatever. 68.2 is fine. What's the probability that my z-score is greater than 0? There you go. Hopefully that is 50%. But now here, I don't know exactly, right? I know where my boundaries are. And so again, if I asked you from -2 to 2, right, that would be your empirical thing again. Right, your 90, what is that, 94? I always have to look it up. Let me go flip back, 95.4, right, if it was between -2 and 2. But what if I don't ask you one of our empirical rules? This is what I'm going to need, my calculator. So where is a z-score that is 1.23? Right, that's about here, right? Positive, because we have 1, 2, 3. So there's approximately 1.23. What's the probability that my z-score is greater than that? Where should I shade? This is what I was trying to jump ahead to, is trying to highlight what you should shade, and that's what I messed up on part A here. This is where I wanted to, this is what tells you where to shade. So you draw your z-score and then you shade either above or below that line. Remember, your line has no dimension. So I'm shading above that line. Do you expect that percentage to be bigger than 50% or smaller than 50%? Smaller, right? So how I do this on my calc, so you already know what you're expected to get. How you do this on your calculator is you do your second vars, choice 2, and then it will ask you your A and your B. Your A is the low, right? The low end or the left end. and the B is the right. Think start, stop. So where are you starting here? Where do I want the shaded area? I want to start and stop. So start at 1.23. Technically, you're going to stop at infinity, but you can't enter infinity. Your calculator is just approximating. So in place of infinity, I don't know, put, I don't know, 10,000 maybe. Right? And you get close enough. Just wanted to verify that I got down. I can't read my writing. So I got, using my calculator, which I do not write down, by the way. I just do my drawing and I write down here 0.109, 3 places past the decimal, or 10.9%. I don't care which one you give me, percent or decimal. So how about this one? What is the probability that your score will be less than negative 2.03? So you want to draw where you think negative 2.03 is, and then you want to shade. So from your strip, it says shade less than your strip. So again, I expect a pretty small number. Now here's the issue. When you're entering it into your calculator, where are you starting this time? Technically, negative infinity is where you're starting, and you're stopping at negative 2.03. What are you going to put in for negative infinity? Yeah, negative 10,000. Okay. I got 2.1% when I was done hitting this on my calculator, which goes along with check. What about this one? How do you think you're going to do this? Negative 1.5 is maybe here-ish, and positive 0.08 is here. So I want this area. Well, just use your calculator. This time you don't have to worry about a 10,000, right? You're going to enter a negative. You're going to start at negative 1.5 and you're going to stop at 0.8. Again, I can't read my writing, so I got to type this in actually. So negative 1.5, comma, 0.8. And I got 72. Oh, that's what my writing is. What is this? What does that absolute value mean? Right? Absolute value means that you are, right, positive or negative. So this is saying, right, you're between 1.32 and negative 1.32. So that's here, negative 1.32 is about here, and 1.32 is about here. So is this what I want? Is that the right area? Whoa, what is your shading asking you? You're saying the probability that Z is greater than 1.32 or what? So this is not right. What is the probability that my Z is greater than 1.32? As well as what is the probability that my Z score is what? Because of the beautiful symmetry, though, what can you do? I could just find this piece or this piece and double it. So I could just do 2 times this probability or 2 times this probability. Use symmetry of the graph when you can. So what did I get? Use my 10,000. Whoops, I typed negative. See, I did something wrong and I got like a 90%. And I was like, that can't be. So I 2 times 0.093 and I got 18, almost 18.5%. A little bit more than 18.5%. 18.7. Okay. Forgot that I put those in there. So again, when you don't have an actual boundary, this is what you are typing in place of negative infinity, infinity. I haven't tested, I just tried 10,000. I don't, and it's close enough when I compare to my Z table. So I'm good. Now, these are the kind of problems where you are given your Z value, right? You are given the Z value that you want to find the probability, and you're finding the probability that your Z score is above, between, below, blah, 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 blah. But these next problems go the other way. So this time, what if we're given the probability? Can you find the Z score? And again, the calculator, if you hit second vars again, you'll see choice 3 is the inverse of the normal. Once again, you do not have to worry about these 2 values. That is your mu and your lowercase sigma, your mean and your standard deviation. Your calculator assumes the 0 and 1. So the only way you would have to enter is that if we are going to shift or adjust either one of those, and we're not going to. But here's the really important part for making sure you interpret what your calculator is saying correctly. All right. I'm not going to interpret that. I'm not going to interpret what that is saying yet until we do some examples. So this is the opposite, where I'm going to give you the probability and I want you to find the value, but I have to be careful. So I like to think that. What is the probability that my Z score is less than, I don't know, if 63% is shaded? That's what that's asking me. So if I cover 63%, there's 50. 63 is somewhere like that. So I expect a Z score that is positive. That's what I'm after. So use your calculator and you hit the 3, and all you have to do is hit one number, which is 0.63. .63, so you hit the area. What's the Z score that you get? 0.33. Does that make sense? Right, 63% of the data, right, laying there is pretty close to the mean, right? It's just above, right? It's above 50%. 50% would be a Z score of 0. Right? So believable. Check. I'm going to skip B and D for a minute because those are the ones where I have to worry. So hopefully you can see what I've highlighted and why I have to worry. So let's do C. Given a probability, oh wait, duh. Given a probability of 50%, what's your z-score, right? If you've shaded 50%, oh, that's a terrible drawing, by the way. If you shaded 50%, what's your z-score? Hello. Still terrible. Zero, right? Duh. All right. So here's the issue. The reason this is an issue and the reason why your drawing is super important. Read it first and say to yourself, what is the z-score if I've shaded 37% of the area? 37% is not 50. So I am shading here. I want a z-score where a z greater than, right? The z-score is greater than. So where are you shading? 37% has to be to the right of your z-score. So where I'm shading matters. I want a z-score where the shaded area is only 37% of the whole curve. But that shaded area is to the right because I had greater than, right? Just picture what you would do in the last slide. If I had put a number here, you would have drawn a strip and shaded to the right of it. And then you would have figured out your probability. So this z-score better be positive. But go ahead and try to do your inverse normal with 0.37. What do you get? A negative. You know the z-score has to be positive because of your drawing. So that's what this means. Your calculator is always reading from the left tail. It is treating 37% from the left. You got a z-score of negative 0.33. Guess what z-score you really want? Positive. Let's look at the next one. I have a greater than situation. If I was doing this in the last slide, I would draw a strip under the curve and then I would shade 63% of the curve to the right. So to get 60% of the curve drawn to the right, where are you going to put your strip? Somewhere here, right? Right, pun intended. There's about 63% of the area. And don't quibble with whether it's we're just approximating. But the point is, my z-score should be what? My z-score should be negative. Well, what happens when you do your inverse normal with 0.63? You already know what you're going to get, right? You're going to get what you got in part A. You're going to get 0.33. But is 0.33 what I want? No. I want negative 0.33. So what's the pattern? What's the pattern? If you have a greater than and you want to use your inverse normal, negatize your answer, baby. Okay? Your picture will also help you to remember what you need. All right. So there is a homework handout that goes with this video, and most of your work is going to be using your calculator to get the actual answers. When you're doing a problem like this and you're going to ask me, what's the setup? Well, there really isn't. There really isn't much setup. If on an assessment I ask you, I'm going to put a point value on the sketch, I will ask you to make one. So unless I ask you here in these directions, I didn't ask you. The only thing I'm sorry. I did ask you to sketch it. I did ask you to answer this question, and then I asked you to compute. But if I just gave you this problem like it is, there's not, right? You're just going to give me the answer. Okay, my Z. All right.